Assalamu alaikum. In this series, Mr. Omar will guide you through some practice problems to cover all items included in the coverage issued by Emirate Schools Establishment, E.S.E. This is part 1. Have a fruitful time.
Bismillah ar-Rahman ar-Rahim. Welcome to this series in which we will discuss some practice problems according to the Coverage Physics Exam Term 2, Year 23-24 for the grade 12. First goal is about the definition of the current. Question 1. If the charge passing vertically through a cross-section of a wire is doubled in the same time interval, what will happen to the current? We know that I equals dq by dt. That means I will be proportional inversely with the time if q is constant. Or I is proportional directly with the q if t is the same. Now we are interested in this one. So we can say that I2 over I1 equals Q2 over Q1. We double the charge, so I2 over I1 equals double Q1 over Q1, which is 2. Then the current is doubled. I2 equals double I1. So when we double the charge in the same time interval, the current would be doubled. Question number 2. What is the current involved when a truck battery sits in motion 720 coulomb? This is the charge Q. In 4 seconds, this is the time. Now I equals Q over T. It's a direct question. 720 over 4. So the current is 180 amperes. Part B. How long does it take 1 coulomb of charge to flow through a handle calculator of 3 milliampere current is flowing? We will use the same equation. We need the time. How long? The time is unknown. This is the charge, 1 coulomb, and this is the current, I. Now, as I equals Q over T, we can write T equals Q over I. For Q, we have 1. And we have current 0.3 milliampere should be converted to amperes by multiplying by 10 to the minus 3. So the time is 3,333 and 1/3 seconds, and according significant figures, it is 3,330 seconds. You can convert it into minutes and hours as follows. Third question, a current in a wire is given by the equation I equals Tt squared minus 3T plus 1 milliampere. Find the charge through cross-section of the wire in time interval between 3 seconds and 5 seconds. Here we need to do some integral, because I equals dq over dt. Now we have the time as a function of time, so dq equals I dt. To find the Q, you need to integrate I on the time. Integration, I it is 2t squared minus 3t plus 1 times 10 to the minus 3, it is milliampere dt from t equals 3 to t equals 5. It's an easy equation. You can integrate by calculator or any method you need. The answer is 2 over 3 t cubed minus 3t squared over 2 plus t from 3 seconds to 5 seconds. The answer is 130 over 3 coulombs. Now question number 4, the same idea. We have a current as a function of time, but we have a graph of it. The current that flows through a conductor versus time graph is given in the figure. Find the charge past the cross-section of the conductor in 7 seconds. The needed time is 7, which is here. And since I equals integration, or QF, sorry, equals integration of I dt, the integration is the area under the graph. So the thing is to find the area under this graph. This shape we have P1, P2, and the height is 4. The area for this section A1 equals 1/2 P1 plus P2 times H, 1/2 P1 it's 3 plus P2 it is only 1. It's from here to here. This is P2. From 2 to 1, 2 minus 1, it is 1. And the height of this shape is 4. So the answer is 8 coulomb. For the second area, we have a triangle A2. It is 1/2 base times the height. The base is from here to here. This is B, which is 6 minus 4, it is 2. And height is this distance, which is minus 5. So this area is 1/2 times 2 times minus 5. It is minus 5 coulomb. So the area under the graph is A1 plus A2. A1 it is 8 coulomb plus A2 it is minus 5 coulomb. The total is 3 coulombs. For the first shape, one can solve it as 2 triangles, this one and this one, with a rectangle. So you can divide this area into 3 shapes: triangle number 1, rectangle number 3, triangle number 2. And the same for the other shape. Now question number 2. We need to define the current density J and discuss some property of it. So to define the current density and what is the unit used to measure it, we can put this information. The current density is the current per unit area flowing through the conductor, or the current divided by the cross-sectional area A. You should note that the current density is a vector quantity. It is a vector, it is not a scalar. The current is a scalar, but the current density is a vector, and its direction is the direction of the positive charge flow, which is with the electric field, and opposites the direction of the electrons flowing. According to this definition, we can put J, the current density, J, equals I over A. The current density symbolized as J, and it is a vector. Now, the unit of the current density, the dimension of the current density, is the dimension of the current divided by the dimension of the area. As units, unit of J is, the unit of the current is ampere, the unit of the area is meter squared. So the unit of the J is ampere per meter squared. This is meter squared, and this one is ampere. Part B, a uniform current of 5 ampere flows perpendicular to the cross-sectional area of a wire with radius of RA equals 15 millimeter. What is the current flow throughout the cross-sectional area with the radius of RP? See the figure. Here we have a figure with cross-section of RA for the whole wire, and we need to find the current in some region of that wire. Let's draw it again. For part B, we know that J equals I over A. And since the current is uniformly flowing in this conductor, we can write J across A, it is the same as J across B. So I through A over the area of A equals I through B over the area of B. Now, we know the current of A, but what about the areas? Area of A, it is pi RA squared, and for B it is A RB squared. Oh, sorry, pi RB squared. We can cancel the pi's. The current flowing through A, it is 5 ampere as mentioned in the question, and the radius of A is 15 millimeter, and for B it is 7.5 millimeter. So here we have 15 millimeters squared equals I cross B, 7.5 times 10 to the minus 3 squared. Again, we can cancel the powers, and we are left with IB equals 5 over 15 squared times 7.5 squared. And this yields to 1.25 amperes. You can solve it easily by this procedure here. Let's write it down here. J equals I over A. So I equals J times A. J is uniform, so I will proportional to the area. So I will proportional to the area, it is also proportional to r squared. Area, it is a function of r by r squared. So we can write the current is proportional to r squared. So I across B divided by across A equals r across B divided by r across A all squared. Let's substitute 7.5, 15 millimeter squared IB over 5, and we will get the same. IB equals 1.25 amperes. Please take care, the radius between A and B, the radius decreases to half, but the current will decrease to 1/4 because we have squared. Let's go to question 3. What is the resistance of a copper wire of length 0.9 millimeter and diameter of 1.3 millimeter? This should be converted into meter by multiplying by 10 to the minus 3. And we have the resistivity of the copper 1.72 times 10 to the minus 8. Now we need to find the resistance R. R equals rho L over A. Rho L over A, it is by R squared. And R is equal to D over 2. So R squared equals D squared over 4. We can rearrange this equation by rho L by D squared over 4. Then it is 4 rho L over by D squared. Put your values. R 1.72 times 10 to the minus 8 for the rho. L it is 0.9 by the diameter is 1.3 times 10 to the minus 3 squared. And the answer would be 0.0117 ohms or 11.7 milliohm, which is 11.7 times 10 to the minus 3 ohms. Question number 2. It is a tricky question. Compare the resistivity. We need to compare the resistivity of a conducting wire with a diameter of 5 centimeters and length of 2 meters with the resistivity of another one from the same material but with a radius of 2 centimeters and length of 10 meters at the same temperature. The thing is, the resistivity depends only on the material and the temperature. It is a characteristic for the material, not for the conductor. So the length of the conductor and the cross-sectional area of it does not matter. Since the both conductor are made from the same material at the same temperature, so they have the same resistivity. They have the same resistivity. Take care of such questions, okay? Now express the unit of resistivity using the SI units. For this question, you can use either of these two equations. Resistivity equals E over J, or R equals rho L over A, then rho is R A over L. You can follow any of these two equations to find the unit of the resistivity. Let's go with the first one. The unit of resistivity is the unit of the electric field, which is Newton per Coulomb, and the unit of J is Ampere per meter squared. So we have Newton meter squared per Ampere Coulomb. But according to Newton's second law, the unit in Newton equals kilogram meter per second square, according to the law of Newton's second law, F equals m times A. And according to the definition of the current, I equals dq over dt, we found that Ampere times second, it is a Coulomb. Put this information in our formula. For the Newton, kilogram meter per second square, and we have here meter squared, Ampere. For the Coulomb, we have Ampere times second. Now deal with these units. We'll find that kilogram meter cubed over Ampere squared second cubed. That's it. It is the unit of the resistivity using base SI units. You will follow your question, since it is a multiple choice question, and see in which stage the question stops. Here or here or here or anywhere else. And you can reach the same if you use this formula. The unit of rho, unit of the resistance, it is ohm. The unit of the area is meter squared, and here we have meter. So we have ohm times meter. This is a very known unit for the resistivity. But ohm itself, now if we need the base units, ohm itself, it is volt per ampere times meter. And the volt is related to the joule by this equation. Delta V times Q equals delta U. This is joule, this is volt, and this is coulomb. So if you put this back here, you will reach to the same unit as this. So the most known unit of the resistivity in all tables in electricity, it is ohm times meter. But I practice this in front of you if they ask you for the base SI units. Now let us discuss some circuits Question number 4, or the goal number 4. A battery with a terminal voltage of 120 volt was connected to a circuit as shown in the figure. Assume the battery has negligible internal resistance. We need to find the equivalent resistance of the circuit and the current through each cell resistor. Calculate the potential drop across each resistor. Determine the total power dissipated by the resistors and the power supplied by the battery. Find Vx. Now, if you note that this circuit is a series circuit, because the current is flowing through the positive terminal. This is the current. It will flow through R5, then R4, R3, R2, R1. And we assume that the voltmeter is very high resistance. So the voltage, the current through the voltmeter almost zero, we can neglect it. Now, it is a series, so to find the equivalent resistance for series connection, R equivalent equals R1 plus R2 plus R3, R4 plus R5. R1 15, R2 25, we have 40, R3 10, it is 50 now, then 20, 70, then 10, it is 80 ohms. Calculate the current through each resistor. Again, we are in a series combination. So, in series combination, we have I1 equals I2 equals I3. They are the same because it is a series, which is the total current. And the total current is the total voltage over R equivalent. The total voltage is 120 over R equivalent 80. It is 1.5 amperes. Now we need the potential drop across each resistor. C. V across any resistor I equals the current through that resistor times that resistor. And we know that all currents are the same, which is 1.5. So V1 equals 1.5 times R1, which is 15. 22.5. V2, 1.5, the same current, times 25. I think it's 37.5. V3, the same current, times 10. It's 15. V4, 1.5 times 20. It is 30. Finally, V5 across R5, the same current times 10, which is 15. If you add all of these, you should get 120. If you didn't get 120, you have some mistake. 2.22.5 plus 37.5 plus 15 plus 30 plus 15. We have here 60, and we have here also 60. It's 120. Okay. Now, determine the total power dissipated by the resistors and the power supplied by the battery. B. The power by resistors, we take the R equivalent, should be I squared times R equivalent. I, it is 1.5. squared multiplied by R equivalent is 80. Yes, it is 80. So the power dissipated by all resistors are 180 watt. You can find the power through I1, R1, and so on, going to P5, I1 squared, P R5, and add these 5 powers, power for 1, 2, 3, 4, and 5, and you will get the same answer. Now the power through the battery supplied by the battery is I times V. I, it is 1.5 times the voltage of the battery 120. So the answer again it is 180. It should be the same because the conservation of energy said so. The last one, find Vx. Go to the diagram to see where is Vx. Vx is around or across R4 and R5. So Vx equals I through x, R through x. And R through x, it is a series. The current, it is I total. And the resistors are R4 plus R5. Go back to the diagram to make it sure. R4 and R5. Vx across R4 and R5, 20 plus 10. Now we have the current is 1.5, 20 plus 10, which is 45 volt. Now we have question number 5. 3 resistors R1, R2, R3, 1, 2, and 2 ohms are connected in parallel. It is parallel. When you solve such questions, first decide what is the connection, parallel or series or a combination of both. The parallel connection is attached to a voltage of 3 volt. What is the equivalent resistance? For a parallel, we have R equivalent equals the inverse of the first one plus the inverse of the second one plus the inverse of third one, all inverse. So we have 1 over 1 plus 1 over 2 plus 1 over 2, all inverse. Don't forget the inverse for the all. The answer is 0.5 ohms. Find the current supplied by the source to the parallel circuit. Here we have different situation than the series. We cannot find that the currents are the same because it is a parallel. So to find the total current, use the total resistance. I total equals V total over R equivalent. Easy like this. The total voltage by the supply it is 3, and the total resistance it is 0.5, so it is 6 amperes. Calculate the current in each resistor and show that these add together to equal the current of the output of the source. Now, for the parallel, we have this fact: V1 equals V2 equals V3 equals the voltage for the combination of them, which is 3 volt. And we know that the current in any circuit, in any resistor, it is V for that resistor over the resistor. So I1 equals V, it is 3, R1 it is 1, so it is 3 amperes. I2, the same voltage, but we have the resistor is 2, it's 1.5 amperes. I3 equals 3 over the third resistor, also 2, is 1.5 ampere. If you add these all together, I1 plus I2 plus I3, you will have 3 plus 1.5 plus 1.5. The answer is 6 ampere. It is the same as I total, 6 amperes. Now we need to find the power dissipated by each resistor. D. The power equals for any resistor I squared times R, and the resistor number I. So let us find these powers. P1, I1, it is 3 squared times R1, it is 1, so we have 9 watt. P2, the current for the second one is 1.5 and it is 2 ohms. So 1.5 squared times 2, it is 4.5. And P3, we have accidentally the same current and the same resistor, 4.5 watt. If you add all of these, P total should be P1 plus P2 plus P3, 9 plus 4.5 plus 4.5, it is 18 watt. E, find the power output of the source and show that it equals the total power dissipated by the resistors. Now, the power of the battery, EMF, equals I total VEMF. The total current is 6 times the voltage is 3. 6 times 3, it is 18 watt. Look, P by the source equals V dissipated by all resistors. So for power, always we have the same equation like this, even it is parallel or series. For the last question, the previous one, we saw the same fact. The power dissipated in series, if you add it, you will find it is the same power and of the source. And here in parallel, the power dissipated by all resistance equal the power of the source. Now let's end this discussion with this question. It is the temperature dependence of light bulbs resistance. This is not in the syllabus, but it comes like this in the coverage. So I want to solve this question. A 100 watt light bulb is connected in series to a source of EMF with voltage 100 when the light bulb is lit. The temperature of the tungsten filament is 2520 degrees. What is the resistance of the light bulbs? Now, we have power and voltage. We can use this equation, P equals V squared over R. We know that B equals E over T, energy over time, or I times V, or I squared V, or V squared over R. Now, rearrange this equation. R equals V squared over B. V is 100 over B, 100 square over 100, so the answer is 100 ohm. This resistor, the resistance at 252 degrees centigrade. I think the question will finish here in the exam. But if we want to proceed for the 20, we can use the relation that relate the resistance with the temperature as follows. R at any temperature equals R naught times 1 plus alpha T minus T naught. Alpha is the coefficient of temperature. For tungsten, it is 4.5 times 10 to the minus 3 per degrees centigrade. Now, isolate R naught. R naught equals RT over 1 plus alpha T minus T naught. Again, this is not included in our syllabus, but it comes in the coverage. I don't know why. RT, we found it 100, 1 plus 4.5 for tungsten, 10 to the minus 3, 5,000, what is the temperature? 2,520. Minus the temperature needed is 20. Substitute and get the answer, which is 8.16 ohm. We will finish with this question. See you in part 2. Thank you.
I hope that this video has enriched you more. In the description box below, there are links to both a PDF document for answers and the other videos in this series. This is the end of part 1. See you in part 2. Salam.